All right, shall we get started? Let's close the. Can you close the door? Everybody here? Okay, so I have a few announcements to begin with. So the first one I gave you like a 2-day extension on the project 4. Some people were struggling with it, and there are midterms going on and so on. So you can do that. People were asking what is the difference between projects and homework. Homework will be more theoretically oriented. Homework is like sort of like the exam, just pen and paper type of thing. There was one so far. There will be more, and we'll be doing more of the theory things when we'll get into like I guess a little deeper theory, when it will make more sense to do more exercises on the paper. There is one more announcement. There is a WebGL lecture today by a special speaker, Ken Russell from Google. And the talk starts at 6 p.m., so that's right after our class. So if you don't have any better arrangements, that this might be a good thing. I just met with him. He's a very nice guy. He's on the WebGL Chrome team at Google. Also, if you are looking for industry positions later on, it might be good to sort of get to know what's going on right firsthand from the people who are doing that stuff. So that's that. Number 3 is the next week we'll have the midterm on Wednesday. So on Monday, my plan is on Monday I won't be here, unfortunately, but I will have you to come and give you solutions to the practice problems, which already been hanging on Piazza for a while. So now would be, as soon as you are done with your project 4, would be a good time to start actually looking at them and recapitulating all the terminology and the basic definitions and how, and especially those are like the dots, right? The terminology and the definitions, and then you need to connect them. That's the logic that connects them. So I don't. Yep.
Do we get a cheat sheet or anything like that?
Oh. No, I wasn't doing that. I don't think that's necessary. I mean, what would that be? I mean, I'm open to discussion if you think that would help you a lot.
Just like some equations.
Like definitions, I guess.
Like what a DCT is, like
What is like a linear space and so on. It's an interesting idea. I mean, I certainly didn't do it last year. The thing is that, okay, here is the thing. I think if you don't have it in your mind, the definitions, then I think the cheat sheet is not gonna save you, because you will only have like this one lecture for it. So if you don't like remember what is a subspace, you have to go to your cheat sheet and then you start thinking about it, then I think it's a little bit too late. I mean, yeah. It's not a lot you need to remember here. Yeah, so by default I was thinking that only pen and paper is allowed, so no like books or even calculators or something. There will be like some computing, but sort of like the type of computations I am doing here when I'm like showing you some examples. So it's like 2 minus 1 times 3 type of stuff. It's easy to make mistakes in that, so you need to be careful. You need to be aware of the fact that humans make mistakes and then check for them. Like the same applies in programming. Yeah. Any other questions on this organizational matters? If not, we will go back to least squares, which I started the last time by discussing a projection onto a subspace. I think the last time we discussed projection onto a 1D subspace, right? So let's quickly recap that. Now, as I'm thinking about it, you really need to know these things, like what is a basis, what is a subspace. Maybe I can do some sort of summary on Wednesday if you would like. Looks like you would like that. So let me think about some more. So let me remind you, what did we do the last time? What did we do? We had a 1D subspace only, right? So there was zeros somewhere. There was some vector A. And we were debating about a projection of a vector B on that subspace, or in general any vector. How does it look like when it gets projected? And by projected, I mean I orthogonally drop it onto the subspace, right? So if this was if I tilde it and this was my Earth, this would be where it would fall under. Oh, you should tell me that you don't see nothing. Okay, sometimes it goes out of focus. Okay. So if this was Earth and I dropped the vector b on the ground, where it would land, that's the projection, right? So do you remember what was the formula? That was a matrix. It's a linear operation, and we derived last time we derived the matrix form for it. Does somebody still remember it? Now things like this, actually here's the thing. Some things you don't need to remember the things you can derive from other things, right? So like a matrix of a projection, remembering that would be silly, because if you need to, you can just like write few equations and derive it. That's what I did the last time. So I don't want to do it again unless you want me to. I just want to see the result. So what is the linear operator, such that if I apply b, it gives me the projection. So I guess I denoted it before as b parallel, right? Anybody remembers that? Something with a t. Actually, I don't know if I remember it. Probably don't remember it myself. I would need to derive it too. So the operator is like this, ATA. And mind you, A by default, I mean this is a column vector, right? So on the top you have the outer product. We talked about outer product last time. And in the bottom you have an inner product. So this is a scalar and this is a matrix. So altogether it's a matrix, and it's the matrix of the projection operator. The operator takes b and projects it onto the b ortho, not ortho, sorry, the b parallel part. And what we will do today, we will generalize it onto a projection onto a subspace. So this was a projection onto 1D subspace, and today we will generalize it to projection onto arbitrary dimension subspace, so large subspace. And that's important because that gives us an idea how to solve overdetermined systems of linear equations, right? I think I broached this a little bit last time. So if I have a system of equations like this, you can immediately smell that there is something fishy about it, right? Because if I have 3 equations and just 2 degrees of freedom, that's the case here. I would have to be incredibly lucky for that to have a solution, right? It's not impossible. We discussed that under some circumstances, it indeed might have an exact solution, but it's probability 0 type of event, right? If I slightly perturb some of these things, then the solution will probably go away. Because intuitively, what you are really asking for, you have only 2 knobs to tweak, and you want 3 things to match, right? So that quite often does not have a solution. So this system, for example, does not have any solution, right? And I think the last time at length I was saying, well, but this is not good because we want to compute something like a solution, the next best thing to a solution. And because this is often useful in like engineering practice and so on, because maybe the system does not have a solution only because of some small errors, or maybe even the error is large, but it still makes very good sense to be asking for what is the next best thing to a solution, the closest thing to a solution you can get. You can't get a solution, right? We know that. You know how I hope you know how you would show that the system does not have a solution. That's what we discussed when we discussed solving general systems of linear equations, the rectangular thing, right? You remember it depends on the right-hand side and so on. So I guess I'm doing a little bit of recap for the midterm. Maybe let's leave it for Wednesday better, and let's do this properly first. So what do we do if we cannot get a solution? Well, the next best thing is the least square solution, okay? And the least square solution simply says, well, if I can't get this exactly, such an x basically doesn't exist. I can forget about this. But instead, what I can find is an x which minimizes the norm of ax minus b. So it gets as close as possible to b. It will, if it had a solution, then this term would be exactly 0, right? That would be nice. But in our case, we can't get exactly 0, so we can be asking, well, what else? How close can we get, right? What error? If you interpret the ax minus b as an error, what is the minimal error we have to accept if we have if this models some real world problem? Okay. So there are. Oh, let me give you a graphical picture of it. Yes, you know I always like to draw things graphically. So what does this mean? Yeah, graphically is this. So let's do a 3D example. So example of least squares in R3. Let's say I have a plane, and let's say I have an orthonormal basis here called A1, A2 and here would be A3. I guess they should have all the same length if I said orthonormal, but it doesn't matter. And let's say I have some vector B here. You know what, and let's make it very simple. Let's say that A1 is just the first standard basis vector, so it will be just 1, 0, 0 to make it concrete. And A2 would be just 0, 1, 0. Okay, so this is just the standard basis vectors in the plane, right? Very, very easy thing. And let's say that B is, for example, 2, 3, 1, right? So something like this. I go 2 lengths in A1, 3 in A2, and 1 in A3. That's my B. And now I want to be solving the system, the 1, 0, 0, 0, 1, 0 times x equals B, right? So B is 2, 3, 1, right? So quite obviously, and x is like, x means x1, x2, of course. X is 2-dimensional, right? So you can clearly see that there's no solution. No matter what I'm gonna do, there's no way I would create 1 by multiplying zeros and adding that together, right? Obvious, right? So what is the best thing I can do? What is the least square solution in this case? In this case, it's sort of easy to see, right? What do you think is going to be the least square solution? What is going to be the x1 and x2 of the least square solution? So yep.
2, 3.
Exactly. Yeah. The least square solution will be 2, 3. Write it here. Makes sense, right? And if I do this, I will not get to 2, 3, 1 where I wanted to get. Well, I will get to 2, 3, 0, and it's the best thing I can do in this subspace, right? Because again, geometrically, you can look at it as taking linear combinations of the vectors A1 and A2. So you can generate any point on this subspace, on this plane here, right? Clearly, you will not be able to get to B because the B goes out of the plane, right? But what you have suggested here is the right thing to do. So here is my 2, 3 vector. And it does have some error, right? There is still the entire 1A3 vector missing there, but that's as close as I can get to B. And that's really the point of the least square solution. Okay? So I'm constrained to some subspace. I would ideally want to get there. I cannot really get there exactly, but I will get there as close as possible. That's the least square solution. Okay, makes sense? And in general, it's the same idea, except that it's multiple dimensions, so I cannot really draw pictures like this. Okay, so there are two. Is that clear? I think this is a very simple thing. Now, notice I was like being easy here, so I picked an orthonormal basis here. So that looks trivial. Indeed, if you have a least squares problem and the column vectors of the matrix are orthonormal, then the solution is incredibly simple. It gets more complicated if these vectors were not orthonormal to begin with. If it was some general matrix, like in this case, right? Then we need to do a little more work to find the least squares solution. So let's take a look. How can we find the least squares solution in general? Okay. There are two approaches to it. I would like to give you both of them so that you can compare how do they relate. So the first obvious one is to just compute the solve an optimization problem, a quadratic optimization problem. So find an x that minimizes this objective, right? That's what I said. That's the idea behind the least square solution. That is basically such x that minimizes the square difference between ax and b. Okay? Do you know how to do such a thing? So first, this is like an instance of an optimization problem, right? When my objective function fx, where x happens to be, maybe I can give it like a little arrow to highlight that it's a vector, right? So x in general, we are in n dimensions, so it's an n-dimensional vector. And A would be an m by n matrix, right? Typically m would be larger than n, but in theory it can be anything. and b would be an m-dimensional vector, right? So fx is a function that goes from, so f is a function going from Rn to R plus, right? It's trivial to see that this will never go below 0, of course, it's a square, right? So it's bounded from 0, right? So you can immediately sort of see that this thing must have some solution, because going to infinity is not going to be an option. It's an unconstrained optimization problem, right? It's bounded from below with 0, right? And if the norm of x goes to infinity, that means that you are only increasing it, at least in, okay, the argument gets a little more subtle, but you can sort of see that it has a solution. You would have to show that it is bounded level sets and so on, but let's not go in that detail. So what we can do about this, so it's an, let's try to solve this optimization problem, okay? So my objective function is f, so if I write it like this, so this is my objective function and I want to minimize it. So what I do, I just rewrite it using the dot product, right? And I just expand this, okay? Have you seen this before done, by the way? It's like a, okay, let me ask differently. Who's seen this before, this derivation? Okay, probably nobody. Well, that's good. I was worried if it's not something too basic, but ATAX. So, or shall I do it slowly then? Okay, I'll do it I'll do baby steps. Okay, so I will do XT AT minus B transpose. So I transpose this whole first thing. Here I have AX minus B. Then I just multiply it out, so I'll have get XTATAX, and here I will have BTAX, and here I will have XTATB, and here I will have BTB, okay? So you can see that there is a quadratic function in X emerging. So I can simplify this a little bit, because I said that B is an m-dimensional vector, right? It has to be. So what is the type of this thing? So I have BT, that's a row vector, right? So maybe let me write it like this. B is 1 by m, A is m by n, and X is n by 1, right? So altogether, it's what? This product BTAX. 1 by 1, it's just a scalar, right? So scalar, so it's a 1 by 1 matrix. So scalar I can definitely transpose and I will get the same thing, right? That's the funny thing about scalars, the transposition doesn't really do anything, right? But if I transpose the same, so BTAX equals BTAX transpose, because it's just a 1 by 1 matrix or scalar. And if I do the product rule of transposition, I will get that this is this. So that's the same term as here, which allows me to put both of the terms together. Since you haven't seen it before, I'm doing it slowly. So this will give me minus 2x transposed ATB plus BTB. All right, so I put them together because I can transpose one of them and add it to the second one. Everybody got it? So this is the function I need to minimize. So you can already see that this term there does not play a role, right? Because the only thing I can be changing is the x. So this is just a constant, and I'm looking for x that minimizes this. So this constant does not really change, does not make a difference in the x that minimizes this, right? So I could as well forget about this term. It's a constant term. And how do you, if you had some calculus, most of you did, how do you minimize a function? In this case, it's actually nice because it's a quadratic and convex function. Why is it? Okay, I think I didn't discuss these things properly, but you can believe me that's a convex function, that the matrix is positive semi-definite. We will discuss that later. For now, you can just believe me that's a convex function. And a convex function you can perfectly minimize by doing what in calculus? Exactly, yeah. Take the derivative and set it to 0. So here I'm dealing with a multivariate function, right? So instead of derivative, I need to take the gradient of it, but that's no problem. So if I take the gradient of this function, I will get this. I'll get 2ATAX minus 2ATB. So this BTB goes away because it's constant, so the derivative makes it disappear. If you don't know these matrix calculus things, then don't, or do you, or don't? Does somebody know this? Probably not. Yeah, I usually do it as like a last lecture when like explain connection of linear algebra and calculus. It's actually easy if you don't want to believe me and you want to verify this, you can just write it per component and just do the derivatives in the usual way. I just did it quicker here in the interest of time, and this is indeed true. This is how you differentiate matrix expressions like this. Okay, so this is the gradient of f, and next step is that I set the gradient to 0, right? So I say that 2ATAX minus 2ATB has to be 0. So I can as well get rid of this 2 here, right? Because it's just a constant. And I will arrive to this expression. ATAX equals ATB. Okay? And this is a relatively famous or well-known system of equations called the normal equations. And this is now something we can solve. It's particularly simple if ATA is invertible, because what is the dimension of ATA? So A was m by n, right? So ATA is n by n, right? So this is just a square matrix, right? So now I can be talking about inverting the matrix, right? And solving this system, now a square system of linear equations, gives me exactly the least square solution. Okay? Now there is, so this is like the calculus or mathematical optimization, like the baby mathematical optimization way to arrive to normal equations. And there is a different algebraic way to arrive to normal equations, which is, well, maybe even simpler. I mean, writing the math is simpler, but maybe you need to do a little more thinking around it. So let me show you also the algebraic way how to derive the normal equations. So maybe it's good to go to this picture, and we will arrive to the same set of formulas, but just from a linear algebra perspective. So here, what we are looking for is the least square solution. So if the least square solution is called x, then what I'm looking for here, how would you define, without any optimization now, like forget about like this minimizing this objective sort of thing. You can just reason about it geometrically. It's sort of nice that these two things connect. So how would we characterize the solution x just in terms of what we know about linear algebra, such as orthogonality? Now I already gave you the clue, that's orthogonality. So again, I'm in the same situation, right? I'm looking for a least square solution for a system of linear equations. The A1 and A2 here are the columns of the matrix of my system. So what does the least square solution need to satisfy? What are the conditions in terms of orthogonality? Does anybody have an idea? You do?
The solution needs to be orthogonal to x.
What needs to be orthogonal?
The solution, the least square, the distance between x and b.
Yeah, that's right. So we need to look at this thing, the error, right? So I guess I wrote it in a little bit confusing way. This should really be ax, right? Because the x is just the coefficients. I need to multiply the a's with. So this is really ax. So indeed, I can say that like my error, let's denote it as e, is the ax minus b, right? And what you suggested is that that this error must be orthogonal to a1, and I suppose you also meant that the error needs to be orthogonal to a2 at the same time, right? Because it sort of makes sense, right? Because the error is what I want to make as small as possible, right? And it will be as small as possible when it's or exactly orthogonal to the subspace generated by A1 and A2. If we want to practice our subspaces, we can equivalently say that this means that E is orthogonal to the span of A1 and A2, right? It's saying exactly the same thing. Okay. Because clearly, if you break the orthogonality here, if you move it a little bit away, then this B will get only bigger, right? That's basically like a Pythagoras theorem or something, right? It cannot get smaller than this; it can only get bigger by perturbing it. So what do we get if we think about it this way? Well, I think I have this on a slide. Yeah, right. I have this on a slide. So this is the linear algebra perspective. So we call this the error, the E, and that will be the AX minus B. And what we want is that the E is perpendicular to all the column vectors of A. Okay, that's what I draw before on the 3D case. Okay, so this should be capital E because it's a vector. So if I can write it using matrix vector product, the system of equations, right? I can just write that ATE must be a vector of all zeros, right? Because again, it's multiplying all the columns of A. Everybody sees that? And then all I need to do is remember that that E was defined as AX minus B, right? So just plug in AX minus B to E, and I get this. I get ATAX minus B equals 0. But that's exactly the same what we derived before using calculus, right? Because if I write it out, I'll get ATAX minus ATB, which I can put on the right-hand side, and I have again the normal equations, the ATAX equals ATB. It's exactly what we derived here before. So this is like the linear algebra way how we can get to it. And again, even in higher dimensions, it's true that the least squares solution is the projection of the vector B onto the span of A. That's why linear algebra is really useful, because it lets you reason about higher dimensions, right? In 3D, it's easy to sort of imagine what's going on, right? If this has 1,000 dimensions, like your 10 or 100,000 dimensions, like your images or audio signals you are working now with on your project number 4, then you need to rely on the linear algebra to make sense of it. Okay, so so far we have arrived to the normal equations. Is that clear to everybody? Using 2 ways, which ended up giving us the same thing, which is good. So now we need to solve them somehow, right? Actually, maybe before, let's see. Well, let's talk a little bit about this ATA. The ATA is a sort of famous type of matrix, because that's sort of the way how you can convert, if you want, like, intuitively. It's a way to convert a rectangular system into a square system, essentially. And this matrix ATA, it even has some names. I think it's called like the Gram matrix sometimes, or covariance matrix if you are in statistics or something. And it has some interesting properties. So let's take a look at some of them. So the first one is obvious, right? I mean, I already said it, that ATA is going to be square, right? Now, ATA is also going to be symmetric. Did I define symmetric matrix? I'm not sure. I mean, symmetric matrix means the matrix M is symmetric if and only if the transpose is the matrix itself. So the transpose doesn't do anything to it, right? Like in 2D, symmetric matrix means this, right? If I transpose it, it doesn't change it, right? In 3D would be A, B, C, B, C, D, E, E, F. That would be symmetric matrix in 3D. Something very simple. Okay. So it's easy to see that ATA is symmetric. It's probably easier to write it because we know we have this rule for transposition, right? So if I have matrices M and N, and I transpose them, I get NT, MT, right? So what happens if I transpose ATA? So let's imagine that AT now is in the role of M, right? And A is in the role of N. So I will get A transpose, that's my N transpose. And there's A transpose transpose, but transpose twice just gives me back A. Do you see it? I just got the same matrix back. So indeed, ATA must be symmetric. Yep. So those are the easy things to realize, that it's a square and symmetric matrix, which is already nice. And there is another beautiful property which says that the null space of ATA is exactly the same as the null space of A. Okay, remember how we talked about null spaces and that they are important when we are solving systems of linear equations, right? So, and what we want to be we ultimately want to be solving this system of linear equations, and it has a very special matrix. So we can, and it turns out that the null spaces are exactly the same. So how do we prove it? So here is how do you go about proving that. So we need to show that NA is exactly equal to NATA, and we do this by showing two implications. So first we show that all that's in NA must be also in NATA. So if I take any vector from the null space of A, it must be also in the null space of ATA. And then I show the other way. So this way I would just get this inclusion, right? It could also be bigger, the other one. But then I show the opposite one. Then I show that whatever is in ATA must also be in the null space. Whatever is in the null space of ATA must also be in the null space of A. And from this, I have to conclude that they must really be the same. Okay, so let's see how it's done. It's not very difficult. So this one is actually trivial. So if I have an x in the null space of A, so that means that AX is 0, right? And I can certainly multiply this with AT from the left, both sides of the equation, right? So I get ATAX, and this is AT0, but whatever times 0 is 0. So this means that ATAX is 0. That means that x is in the null space of ATA, right? That's the easy part of the implication, right? That shows me that this part, that the null space of A is a subset of the null space of ATA. And the other way around is also simple, just a little bit trickier. So on the other hand, if I have something in the null space of ATA, that means that ATA, let's call it y now to not confuse it with the first one. So that means that ATA y is 0, right? Because it's in the null space of ATA. So what I can do, I can multiply it with yt, both sides of the equation. So I get yt ATA y, I get yt 0, that's still 0, right? And here the argument goes like this. So this yt at ay, I can write as ay transpose ay, right? Because I can just use the transposition rule, the multiplication of transposes. It swaps the order. And this turns out to be nothing than the norm of ai squared, ay squared. Okay? So this was 0, so that means that the norm of ay squared was 0. But the only vector that has 0 norm is the 0 vector itself, right? So from this, I have no other way than to conclude that ay is 0, right? And that means that y is in the null space of A. Okay? So this is perfect proof. Sometimes I cut the corners in the proof, but this proof is like perfect. Like I don't think any mathematician could object to anything like that, because it's fairly simple. And it's nice. This shows that the null spaces are exactly the same. And that's going to be helpful when we will be solving. That has an important consequence, important corollary, which I will get to in a minute. Okay, so is this clear? Why the null spaces are the same? Great. So here is how it makes most sense. So here is how we can solve the normal equations. So let's first consider the simpler case where the matrix A has full column rank. Okay. That means because I assume that my m is larger than n. By the way, that makes sense because in rows I usually have my data, my measurements, and in n is typically like the dimensions of my model, and it's always easy to generate plenty of measurements, right? Especially in the big data age, if you will. So m is gonna be certainly larger than n in most applications. But it doesn't even matter here. It will work anyway. So let me assume that A has full column rank, so that's equal to n. And that means because the null spaces are the same, so if the rank is n, that means what is the dimension of the null space? There's formulas for that, right? Well, if it has full column rank, that the dimension of the null space is n minus n, that's 0, right? Makes sense. It doesn't have any free variables if it has full column rank, right? But we know that the null spaces are the same, right? And this is an n by n matrix. So that means that this matrix must also have a null space of dimension 0, right? So that means it's rank n and therefore invertible. Okay, so if I start with a full column rank rectangular matrix, then my ATA is invertible. And what I can do is to write the solution of the normal equations. The normal equations were, let me write it here, ATAX equals ATB. And if I can invert it, I'm almost done, right? I just invert it, and this is my least square solution. Okay, and this is such an important matrix that it has a name. It's called the pseudo-inverse. Sometimes it's denoted like this, like with like a plus or like a cross mark or something like this, and it's called the pseudo-inverse, and it's exactly this. So this is, by the way, the least squares. You can also understand it as a generalization of inverse, because I was always saying there is no such thing as inverse for rectangular matrices, and that's absolutely true. So the next best thing to inverse you can do is the pseudo-inverse, which gives you the least square solution, right? So you can see the pseudo-inverse is an operator that computes the least square solution for me, right? In other words, if I have a constant A matrix and there will be more and more right-hand sides B coming at me, someone will be throwing B's at me and will want me to quickly compute the least square solutions, I can just compute the pseudo-inverse once and then just do matrix vector multiplication. Very quickly return the least square solutions, okay? I just had this discussion with a PhD student of mine who's gonna do exactly this. In some cases, it's like really what you want to do. In other cases, it would be silly to be computing the inverse if it's sparse and so on. We sort of discussed this a little bit before. But those are the numerical details. The math works like this. Okay. By the way, the full column rank assumption would certainly not work for a matrix like this, right? If it's the short and fat matrix, there is no chance it could have full column rank, right? You know that by now. Okay, good. So here is the cool thing. Even so, what can we do? So let's talk a little bit. I don't have a slide about it, unfortunately, but let's talk about the case when A does not have full column rank, right? For example, it's a matrix like this, or it's even like this nice, tall and skinny, good-looking matrix. But for some reason, it happens that the columns are linearly dependent, so we don't get a full column rank. Okay. So in this case, what happens to the least squares and the normal equations? Here is a cool thing. So we know that NA, the null space of A, is a subspace of Rn, right? And ATA is also a subspace of Rn, right? So they are both subspaces of the same space, right? And remember, now it's going to be useful what we discussed at the 4 fundamental subspaces theorem. What was the orthogonal complement of the null space? So let's start with A. You still remember what was the orthogonal complement of the null space? We discussed this at length when we discussed the 4 fundamental subspaces of a matrix. So now it actually becomes important when we actually need to solve some system of linear equations. So the orthogonal complement of the null space is the row space, right? aka the column span of A transpose, right? If you don't remember this, it's not so hard to derive it from basic principles. So I guess you don't really have to try to memorize these things, but if you do, I guess it can't hurt. So the same way, the orthogonal complement of the null space of ATA is the column span of ATA, right? Because this matrix is symmetric, so transpose is the same thing, right? Well, but wait a second. These null spaces are the same, right? And their orthogonal complements are uniquely defined, right? So that leaves no other conclusion possible than the column spans of AT and ATA are the same. Okay? Even if A does not have full column rank, I didn't need that assumption anywhere there. Okay? And what does that mean? That means that the system of least squares equations, the normal equations, that means that it always has a solution, right? Because look, the right-hand side is something in the column span of AT, right? And I know that the column span of ATA is the same, right? So whatever I've generated from AT, I can also generate from ATA. So that means I am always able to find a solution. I guess that sort of makes sense from the optimization perspective. Because as I sort of started with this optimization perspective, when I'm minimizing some function which is bounded from below with 0, and I cannot have an increasing, I cannot go with x to infinity and expect this to be decreasing, I'm just saying it informally, then it just must have a solution somewhere, right? So that's, again, that's sort of cool if you think about it. It's like an optimization way to see it, and this is the linear algebra way to see it. So like 2 viewpoints on the same problem. Unfortunately, they both agree in the conclusions. If they didn't agree, I probably would have a bug somewhere, right? That's, by the way, also the best way you can check for things. Just do it in another way and see if all things still add up. Okay. So what does it mean in the case A does not have full column rank? So I still have a solution, right? But what is the difference from this case? Do you see that? This case I had a unique solution, right? That was just exactly 1x. I had an operator here, the pseudo-inverse, that gives me exactly that 1x, right? In the case when A does not have full column rank, what's gonna be the difference? I mean, again, I need to solve this, right? But in this case, ATA is not invertible, right? So what I'm gonna do about it, now you should know how to solve a general system of linear equations. In particular, this one. You know the solution is going to exist, but what's gonna be the catch? It's not gonna be unique, exactly. There's gonna be an infinite number of solutions, right? And if you remember what we discussed about solving systems of linear equations, you know that you know how to write them all, right? You just find the null space, you find one of the solutions, then you plug whatever you want for your free variables, and that gives you the entire space of the solution, the null space of ATA. Okay, so that is this. Oh, let me give you a few more comments on this. Another piece of paper. So if I solve it, oh, maybe here. So if I write a solution like this, if let's just make things simpler and assume for a moment that we have full column rank. So my solution is uniquely determined by ATA inverse AT. So these are the coordinates of the least square solutions. If I want to get back the projection onto the subspace, all I need to do is AX, right? So if X is a solution, then AX is going to be ATA inverse AT, right? Which I like because it's beautifully symmetric. Do you appreciate the symmetry of this expression? I hope you do. And what this thing is, this is the projection operator. This is my P. So remember what I started with. I wrote this was the projection operator onto one-dimensional subspace. Okay, so I guess I could call it like PA equals this. It was a square matrix, and what it did, it took any vector B I throw at it, and it projects it onto the 1D subspace. Looks like this. That's what we did the last time. This is exactly, or let me try to keep both there. Let's watch this. This is exactly the same thing for higher dimensional subspace. Okay? I hope, do you see the similarity between the two expressions? I could also write this like this. This is a scalar, ATA, right? So I can also write it like this. ATA inverse of a scalar. So this is just 1 over that, but I can certainly write it like this. A, right? Do you see how similar things are? Isn't that beautiful? Because this is nothing but the generalization of this formula to multidimensional subspaces. It's good to keep in mind. If you sort of see the relationship, then you don't really have to remember all that many things because it makes sense logically. Is everybody cool with this thing? Here A was an, let's see if the dimensions match. If A was an n by 1 vector, column vector, right? This is a scalar 1 by 1. This is a row vector. This is 1 by n. So everything is cool here. I can just multiply. Matrix made with multiplication works perfectly. This is just as good as expression as this. This is basically what this reduces to in case my matrix A has only one column. Okay. Quick midterm typo recap question. If I have a matrix m by 1, in what circumstances it will not have full column rank? Because you would probably think that we'll always have a full column rank. I have just one damn column. What can possibly go wrong? What can go wrong? What can go wrong is that if the whole column will be all zeros, right? That will be the only exception when I will not have full column rank, right? If it's all zeros, I cannot find a non-zero pivots, but that's the only exception, right? We discussed about subspaces already, so we just need to dust it off. Oh, by the way, this projection operator has a beautiful property. If I apply it twice, if I do p squared, meaning p times p, what do I get? I will get ATA inverse AT, that's one of them, and the second one comes right here, AT. But wait a second, I have ATA inverse here and ATA here, so this is identity, right? So what this is just ATA inverse AT, okay? So this is just P. So this is one of the funny matrices. I think it has a name which I forgot, so that I don't want you to remember because I don't remember myself. There is some term for it. A matrix, if you raise it to a power, if you multiply it with itself several times, you just get the same matrix back. It doesn't, raising it to a power doesn't do anything. I could do P3, right? I would still get P. I could do P1000, I would still get P. Why? Well, because it's a projection, right? So if I already am in the subspace, it doesn't do anything, right? So if I'm looking at like PPX, only the first PX does something. Once I'm in the subspace, the second projection doesn't do anything. Is that clear? All right. Oh, by the way, let me do this, as I'm in the like a recap type of mode. What if I'm too happy with my derivations and I just keep going like this? So let me do this. There's gonna be a mistake in it. This one actually is on purpose, as opposed to on purpose, not on purpose. So let's see. So I have this rule for inverse, which says if I have two matrices and I invert them, I get N inverse, M inverse, right? We discussed this before. So if I apply it here, what I will get A inverse, A transpose inverse, A transpose, right? But here I have AA inverse, and here I have AT inverse, AT. So both of them are identity. That means that the whole thing is identity, right? So it looks like that the projection operator always is just identity. That's a little bit strange, right? Where did I make a mistake? If I claim that the projection operator always is an identity by doing this derivation.
Why is when you open the inverse bracket, why does it swap places?
This? Why does this work?
The bot. Oh, okay, I see.
Oh, this is a rule for the multiplication of the inverse. It's analogous to the transposition, right? We also had the same rule for the transposition. NT, MT. So yeah, that is correct. That's not the mistake. Yeah.
Because you're assuming A is a variable.
Yeah, and maybe it's not, right? So that that's the right.
So you can't just take the inverse as that.
That's exactly right. Yeah, because the thing is that this projection operator only is interesting if A is rectangular, right? And if it's rectangular, I cannot be writing this, right? Inverse of a rectangular matrix gives me nonsense. That's exactly what I got here, right? Yeah, in the case I had an M by M matrix, if it was square and full column rank, then indeed, then this is true. Then the projection operator is identity, because I'm not really projecting anything. So the projection operator only is interesting if the matrix is rectangular. In this case, this is false, of course. So don't fall in that trap. So that's why I'm saying, I guess I can be saying it as many times as I want, that you cannot really invert non-square matrices, but you will only learn it after you make some mistake and get some conclusions which are contradicting to everything you know. Okay, so I think that I already told you more than enough about these squares. Let's take a look at some examples, shall we? So first example is very nice, very practical thing. If you haven't coded it up yet, I almost guarantee you in your career you will code it up at least once. It's a fitting of a line to bunch of points. So my input, my data, is a collection of 2D samples, x1, x2, x3, whatever distribution. I don't know, those are data. Somebody threw these at me. This would be a y1, right? Here I would have, let's see, make it like this. So here I would have y2, y3, and so on, right? So that's my input. In this case, n is 5. I have 5 data points. Let's imagine you are analyzing something you captured from nature or something like this. What it could be like. This could be like weight of a bear and like height of a bear or something like this, or some data you are analyzing, right? And you see, it looks like they sort of lie on a line almost. And what you would like to do is to find a line which is in some sense closest to the data. You want to fit a line through your data. Okay. If I have 5 data, or even more if I have 1 million data points, it would be very naive to assume that you will get points lying exactly on the same line, right? That's infinitely, that's probability 0 type of event. Like you would have to be incredibly lucky for all the points to exactly hit on the same line, right? Because the line in 2D is fully determined by 2 points, and the remaining ones would just have to happen to be exactly there, right? If this is measured from bears or whatever, it will never be the case, right? or you can put it differently. If that happened to be the case, then you can go after the person who gave you the data and like suspect them from faking it, right? Because you would imagine some error in the data. So what is the least squares fit, the best fit line in the least square sense to the data? That's exactly an instance of a least squares problem, and all we need to do is to stack all our data into a matrix, right? So I'll form a matrix like this. I'll take my x1, I will append 1 here. I'll get x2, and so on up to my xn. That's this matrix here. That's the, so this x means a column vector of all the x's, and the 1 means a column vector of 1's, okay? Here I will have, so my line is, we have been through this many times, right? So if I'm in 2D, then the line is m times x plus c, and m is the, also has some term probably, I don't remember. M is the slope of, oh, slope, yeah, that's the term, and c is the offset of it. So m, if I have high m, then the line is more like this, right? There is one line I cannot represent using this representation. What line is that? The exact vertical line, right? Because in that case, m would have to go to infinity. So in case I was suspecting my data to lie exactly on the vertical axis, I would have to use a different model. But if that's not the case, I can use this model. So, you know what, let me copy it here. So I will do nc. And this sort of wavy equal means at least approximately equal. And here is the other part of my data. Those are my y data points. So here I have constructed an instance of a least squares problem. So if I call this matrix A and call this vector B, computed from your data, now you know how to solve it, right? You compute ATA. This is your unknown, so M and C. And this equals your, ATB. By the way, the way you can like heuristically remember it is AX approximately equals B. I cannot solve it exactly because these are rectangular matrices in general. It's very unlikely it will be a solution. So you just do this. You just hit it with AT from the left, converting it to normal equations. Of course, and now you know why this works, right? Because of all the discussion we have done before. By the way, what is the dimension of the ATA matrix in this example? It's sort of nice. What is the size of the ATA matrix in this case? Well, how many unknowns do I have? What I'm solving for here. What are the parameters of the line? Again, I think it's getting too late and everybody's getting tired. Just two, right? The M and C. Those are the parameters. That's my unknowns, right? So my variables are just 2, M and C. So what is the dimension of ATA? It's 2 by 2 matrix, right? So solving a system with a 2 by 2 matrix, that's really a joke, right? You don't need any MATLAB for that. And the cool thing is, it doesn't matter if I have 5 data points or if I have 10 million data points, right? After I have computed the covariance matrix, the ATA, it just becomes a 2 by 2 matrix, and that's all I need to invert, right? Or if it's not invertible, that's what I need to compute the null space from, and I isolate the invertible component to get the solution. So yeah, so least squares gives you this. So what, a little bit more complicated example, what if your data, well, okay, if your data look like this, you would probably want to be fitting in a line, right? So what if your data end up looking like this, for example? Some sort of wavy thing. It would be sort of crazy. I mean, you could still fit in a line, right? You would get a least square solution no matter what, right? Least square solution always is gotta exist. Even if the points were random, there would be some least square solution, but probably would not be very useful, right? In this case, if I fitted a line, I would just get this, which probably is like a little bit lower, right? Like somewhere in the middle of the point. But in this case, the linear model is probably not a good model for the data, right? If I'm trying to explain the data with some simple model, in this case, like just an affine function, well, sometimes the data just don't look like that would be the right model, right? So what I can do, I can choose a different model. Let's try this one. Give it away. So let's assume that I'm analyzing, I don't know, for this time, like fish populations or something, and for some reason I see if I plot my data in MATLAB that I'm getting something like this, and I come up with the hypothesis like based on some like biology models or something like this. I'm just trying to make it more dramatic. That is gonna be a third-degree polynomial. Okay, somebody suggests, oh, maybe this is like a third-degree polynomial. So can we fit it using least squares or a third-degree polynomial? Somebody suggests that we can. So I want you to not get confused by the fact that we are having x to the power of 3, right? This is certainly not linear with respect to x. But the answer is that yes, we can still apply linear least squares absolutely beautifully, exactly the same way as before. Okay? Because the linearity is not in the model, it's in the coefficients. That's what matters. Okay? I think we have had an example like this before. So how can we solve this? If we want to fit a degree 3 polynomial to my data, how can I do it? Using least squares. Anybody has an idea? What's going to be the difference?
4 unknowns.
For what?
4 unknowns rather than 2.
We have 4 parameters, so there's a C1, C2, C3, C4, right? So from this you can probably guess what the dimension of your normal equation system matrix, what the ATA is going to be like, right? Probably someone else, 4 by 4, right? And the system matrix is going to look just like this. So by this, okay, let me write it maybe more properly. So if my data are again 2D points, right? So my data are x1, y1, x2, y2, and so on. A million data points, doesn't really matter. And what I do, I take the x1, I raise it to the power of 3. I take still x1 and 1. Then I take x2, raise it to the power of 3, x2 to the power of 2, x2 again, then x3, and so on. This is how I get this matrix. Again, pad it with 1, that's for the constant term here, right? So my unknowns are C1, C2, C3, C4. And this needs to be equal to my y1, y2, and so on. So that's it. Another least squares problem. We convert it to normal equations. We solve it. And we get a best fit third-degree polynomial question.
How do these relate to splines? If you have like high enough dimension, or is it just
Yeah, that's a good question. Let's think about it for a second. Splines are also like third-degree polynomials, right? So here, so the immediate difference is here that I want third-degree polynomial defined on the entire domain, on the entire real line, right? Splines work by concatenating, by gluing together multiple third-degree polynomials, right? You could totally do a least squares fit with splines, right? All you would need to do there would be, so if you have your not vectors defined somewhere, you could just, well, okay, it would a little bit trickier because you would have to have the coupling constraint here, right? You have some constraints on the spline which say that the two pieces have to meet and their derivatives have to meet and their second derivative have to meet. So those are the constraints. But then you could actually do, that would be a nice homeworky thing. Maybe I will do it next year for homework or something, to find a spline that fits data in the least square sense, right? Because you need to observe the constraints on the spline, but except for the constraints, you can be finding the spline that fits the data in the least square sense. So yep, that's totally doable. It gets a little bit trickier because you have some equality constraints on top of it, right? So the system gets a little bit trickier. We'll be solving a constrained least squares problem. Actually, as you brought it up, that's an interesting point. Let me. Here is where the optimization viewpoint becomes useful. So here I assume that the x was unconstrained, right? But I could also say that I have some constraints on x. The constraints, the easiest type of constraints is this type of constraints, affine subspace. That's exactly what you would need for splines. And so you will not be looking for unconstrained minimum, but for constrained minimum. And do you know what would need to change in this derivation? So I change it from unconstrained minimum to constrained minimum. You would need to do Lagrange multipliers, for example. There are other methods too. Okay, so I guess I will not go there now because I would sidetrack completely. I already sidetracked a little bit, but maybe I can explain that later. How you get equality constraint minimums, and that's exactly how you could solve the best fit spline curves. Okay, that's a good question. Any other questions? Okay, by the way, when the linearity would break, I was like saying, oh, don't worry about this x to 3, because that's on the data, right? Data somebody threw at you, you can do whatever you want with the data. You can delete the data, for example. But you can also raise them to a third or second power. Sure. When it would break would be if you had a model that would be doing something like C1 times C2, right? Or taking some nonlinear functions of the parameters. Then it would become non-linear least squares. That's also possible, that's also doable, but the methods get a little trickier. Okay? So what I want to do next is to show you like a practical way how to solve least squares problems. And here is the motivation for it. The motivation comes again from the optimization viewpoint. I guess I really like optimization, but I lost my thing about it somewhere. Here. So this was the example I started with, and I told you that if the columns of my matrix are orthonormal, it becomes embarrassingly simple to solve the least squares problem, right? Even in general, if I have, so I'll keep it here just for reference, but we'll go to the general case. So A is m by n now, and I assume that A has orthonormal columns. So you know, we discussed this many times, that's equivalent to saying that ATA equals identity, right? That's an equivalent requirement as having orthonormal columns. So what happens to the normal equations in that case? Well, it happens that basically the ATA completely goes away, right? Because ATA is identity, so I have x equals ATB. That's my least square solution. That's exactly what happened here in this example. That's why you could just shout at me immediately, oh, the solution is 2, 3. I just read it off there, right? But you could also view it like this. You could take the matrix, you could do 1, 0, 0, 0, 1, 0. That's transpose of this matrix. You multiply it by 2, 3, 1, right? And of course, the solution is going to be 2, 3. So if your matrix has orthonormal columns, your life gets really simple, because then the pseudo-inverse is equivalent to transposition, right? Remember my pseudo-inverse was ATA inverse AT. Well, if this is identity, then that means it's just AT, right? That's nice. In this case, the least square solution is incredibly simple. The other way you can interpret it, the only thing that's complicated about the least square solutions is that your columns of the matrix are not orthogonal, right? Making orthonormal matrix from orthogonal, that's easy, but making orthogonal matrix from a general linearly independent columns, that's also relatively easy, but that's the topic of the next thing I would like to talk about, and that's Gram-Schmidt orthonormalization. So we know that if the matrix has orthonormal columns, the solution is very simple. The question is, if we have a matrix that does not have orthonormal columns, how can we bring it to a form that does have orthonormal columns? The other way you can look at it is if I have some, let's try it somewhere else so it's not a mess. So, right, so if I have a 2D subspace generated by some two vectors, which are like unruly like this, so I have two linearly independent vectors, A1 and A2. They certainly generate some 2D subspace, right? Is there a span? And span A1, A2. But I don't like to be dealing with A1 and A2, which are just linearly independent but not orthonormal. I would like to find an orthonormal basis for the subspace because that interests me. And the way I can do it is the Gram-Schmidt process. Schmidt, or Gram-Schmidt orthonormalization. I guess I can get it started and I will finish it on a Wednesday. It's not that complicated of a thing. I'll just give you the high-level algorithm or quickly, and then I will go in more details about it next time. Okay, so the input of the algorithm is n linearly independent vectors. Later I will explain you what happens if you don't have linearly independent vectors, but you have linearly dependent vectors. There is a relatively easy way to fix that. And we are interested in the span of all these vectors, and we want to come up with an orthonormal basis. So the output of the Gram-Schmidt process is an orthonormal basis which spans the same subspace as the vectors A1 to AN. Okay? And how it's done is very simple. The idea is to take the vectors one at a time. So we start with A1. We normalize it to unit vector. The normalization, that's really the easy part. It's to make it orthonormal as opposed to just orthogonal. So that's easy. Then we take the second vector, and what we do, we project away the component of A2 that's already parallel to Q1. So let me try to draw it. We draw it here, so I don't destroy the slides. So I start, so if I have A1 and some A2, so I say that my Q1 is going to be like this, and then from A2 I will split into two parts. I will split it into part in this subspace and this subspace. This one I will project away, and this one I will keep. Then I will normalize it and call it Q2. That's going to be my second basis vector. Then I take the third one, A3. In case it was like a 3D, I would be like pointing out, and I do the same trick. I remove the components of A3, which already are in the subspace generated by Q1 and Q2. So I only keep the part of A3 which is orthogonal to the subspace generated by Q1 and Q2. And I repeat the process until I get a set of orthonormal vectors. Gram-Schmidt deserves a better discussion, so I'll give it a better discussion on Wednesday. But this was the algorithm in a nutshell, and it will eventually lead to QR factorization, which is like a nice numerical way how we can find a solution of least squares equations. Okay, so I think I will call it a lecture for today, unless you have some questions. More likely you want to go, which is okay.